Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and I'm very honored and excited to have this first guest for the 2025 season. It's Dr. Alan Schoenfeld, a distinguished professor at UC Berkeley, the Elizabeth and Edward Connor Chair in the School of Education, a fellow of AERA and a fellow of the American Association for the Advancement of Science, and one of the leading scholars for decades in mathematics education, someone who I've read and appreciated your work since grad school and actually even a little bit in undergrad, but I'm just really excited to talk to you about your career in math education. Dr. Schoenfeld, thanks for being here.
It's my pleasure to be here.
We're going to be talking through several of the ideas that Dr. Schoenfeld has been studying, researching, and contributing to the field. So we have a lot to cover. I'm excited to get into it. I figure we might as well just start right back at the very beginning. When and why did you decide that you wanted to become a mathematics education researcher?
Well, I started as a mathematician. My PhD was in topology and measure theory. And I got a first position as a lecturer at UC Davis, where I encountered the issues that beginning faculty do. I had very, very large lecture classes. I enjoyed teaching very much. I thought about it. I wrote about it as a complete amateur. Had great fun thinking about educational issues, although my career was mathematical. And I talked to a friend of mine who said, if you're really interested in issues of education, you might talk to a guy named Fred Reif at Berkeley, who heads an interdisciplinary group that thinks about issues of the emerging field of cognitive science and what it might do for education. And I went down to Berkeley and I talked to Fred. And it turned out that it was just at the very beginning days of cognitive science. And the issue for me was we didn't know that much about teaching and learning. There was a possibility that we could help make teaching and learning and mathematics much better. I always loved math, and my long-term goal was to have students experience math in the ways that would enable them to become powerful mathematical thinkers and really come to love math the way that I did. So I talked to Fred and became convinced that there was a possibility that that would be a real thing that would happen. I underestimated how long it would take to happen by a factor of 10. I thought I'd give it 5 years to look into problem solving. I had read Polio's work. I thought it was exciting. And I thought, hey, let me give this a shot. And after I've solved it in 5 years, I'll decide whether I want to go back to doing mathematics or stay in education. And here I am more than 50 years later.
Wow. And so that makes me think your grad school experience might have been more of a mathematical grad school experience, and then a dissertation might have been some mathematical things, but maybe just take us into that zone as well with the grad school experience for you.
Absolutely. I was always in love with math and became a math major at Stanford, found the topic I was interested in, which was an oddball little thing. I don't know if you know space filling curves.
Hmm. Yeah, I did some topology. Yeah.
Okay, cool. There's a standard map that takes you from the unit interval to the unit square.
Hmm.
The way you do it is you chop up the unit square into a bunch of pieces and you weave a line, a linear map from the unit interval to the unit square, and then you make a finer and finer mesh.
Yeah.
Well, if you look at that closely, it turns out in the first mapping, each of the intervals in the unit interval maps into a square. If you use the map I use, the unit interval is divided into ninths. The square is divided into ninths. You go to the limit, each interval of length 1/9 maps onto a square of area 1/9. You iterate, each interval of length 1/81st maps onto a square of area 1/81st.
Hmm.
It turns out the map is measure preserving. Whatever length you had on the unit interval mapped onto the same area in the square.
Hmm.
And then you could ask questions like, is that general? There are all sorts of things about piano spaces, which are the spaces that can be the image of something like the unit interval. And the question was, under what conditions, if you can map from the unit interval onto some topological space, under what conditions can that mapping be measure preserving?
Hmm.
And that was the kind of stuff I played with as a mathematician.
Yeah, it is kind of, I remember learning about that the first time in grad school, I think it was, where in school mathematics you always learn the difference between the dimensions, and one dimensional is very different than two dimensional, and you don't want to mix up your perimeter and your area and things.
Mhm.
And then to realize, oh no, there's functions where you can take something that's very linear and just actually make it behave completely like a two-dimensional thing. And for it all to work out function-wise is kind of mind-bending. But I hadn't ever thought about the fact that even the parts of the interval are also themselves mapping onto a little square of the same sort of proportional size. It's amazing.
Yeah, all those things. I mean, ever since I was a little kid reading George Gamow's 1, 2, 3 Infinity, all those interesting properties of infinite sets. And then the Cantor set, which was
Mm.
beautifully pathological,
Yeah,
all
that was
sorts of
amazing
things
too.
happen. That kind of stuff really just got me going mathematically. And I was lucky enough in grad school to have an advisor, Carl DeLu, who gave me latitude to explore the things I cared about. So I wound up being very empowered to look at things that I thought were important.
Hmm.
And that was something that persevered through my entire career.
Hmm. So you have a love for problem solving, you have a love for the things you can do with math, and you also had some freedom to create, I think, a course earlier in your career, right? You had a problem solving course that you designed. And so that leads us into some of your problem solving work that I think you're very well known for in the 70s and the 80s and onward. So I want to maybe ask you about your book, Mathematical Problem Solving. But I know that book didn't just come out of nowhere. It came out of years of starting to delve into this math education research, looking at the cognitive science, metacognition. So I wonder if you could just lay out for us some of those early ideas that you delved into about problem solving and how were you studying those ideas in that era?
Sure. And as I mentioned, I talked to Fred Reif at Berkeley, and I wound up getting a 3 year postdoc at Berkeley where I had freedom to look pretty much at anything I wanted to. When I was a graduate student at Stanford, I had read Polya's work, which I thought was fantastic. And I asked around, and people, I said, Polya's great. I read him, I resonate with him. What can you tell me? And the people who ran problem competitions or coached problem solving all said, Polya's ideas are great, but they don't work in practice. Nobody has ever gotten better at problem solving by working on those ideas. And that was actually the problem that led me to leave mathematics and go into education, because I felt if we can figure out what makes polio work, then I will have significant impact on the problem that I really care about, which is helping people learn to think mathematically. So I took this 3 year postdoc at Berkeley, and I've always tried to mix real world experiences with theorizing. So Fred Reif was a great mentor. He said to me, read until you get sick of it, at which point it's time for you to do experimentation. So I dug into the literature, I got some ideas, and at the same time, I said, look, let me go teach a course on problem solving because it'll be my experiences in the course that will feed my thinking about problem solving. And throughout my entire career, there has been this back and forth. I have some ideas, maybe motivated by the literature, maybe by some laboratory studies. Are they real? I don't know. Let me go in the classroom and find out. Then I'm in the classroom and, geez, something happens. That wasn't part of my theorizing. That needs to be what I focus on next. So I started by studying heuristics, which are Polya's general rules of thumb for solving problems. And it turned out that they were broad descriptions of problem solving strategies. If you knew them, you could use them. But if you didn't, they weren't detailed enough to help you. So take one like if you can't solve the given problem, try to solve an easier related problem. I read that and I went, yeah, I do that. I work the problems in Polya's books and I did that. But it turns out when you look at it more closely, there are 10 or 15 different ways to use easier related problems. And if you're a beginning problem solver, you don't know where to start. So my first work in problem solving was making those heuristic strategies work. And what it meant was taking one of those big names of a strategy, try to solve an easier related problem, draw diagrams if you can, and so on, decomposing them into a family of related strategies. There are 10 different ways to draw diagrams. Which one are you going to do and why? And it turned out that when I did that decomposition, the first thing was I didn't have a dozen powerful strategies a la Polya. I had a dozen groupings of 10 strategies each, but those strategies could be taught and learned. And I discovered how much detail I needed in my problem solving course. So there was this back and forth, starting with the research ideas, testing them in reality. But in the problem solving course, I wanted to document things. So I took videos. I was the first person to have a video camera paid for by the National Science Foundation back in the early 1980s. I took videos of my students before and after the problem solving course to see if I could identify changes in their problem solving.
Mm.
It doesn't make any sense to give them problems that they don't have enough knowledge to solve. So what I wound up doing was giving them problems I knew they had the knowledge to use, like elementary geometry problems from high school geometry. I was in New York at that time, and high school geometry was part of the curriculum. I gave them a very simple construction problem, and they approached it uniformly before the problem solving course as an empirical act. What do you think it looks like? Oh, I bet you this construction will work. You need the diameter of the circle. I was blown away because they should have been able to solve it. The problem, which you've probably seen in the problem solving book, is I give you a pair of lines that intersect. And I give you a point on one of the lines, and I say, I want you to construct the circle that's tangent to both lines with that given point as one of the points of tangency. And every single student that first year approached it empirically. Sometimes they guessed, oh, look, it looks like it ought to be on the angle bisector. Sometimes they said, oh, there's got to be symmetry, so the other point of tangency is the same distance from the vertex. I bet you the line between them is the diameter. They never used any of their proof-based knowledge. And I went back, and the next year, what I did was I had the students solve the proof problems first. Here's the circle. Prove for me that the center of the circle lies on the angle bisector. Prove for me that the center of the circle lies on the perpendicular to the point P. All the students were able to do it. I then gave them the construction problem, and they approached it empirically, ignoring what they'd just proven. Oh, I bet you that line from P to Q is the diameter. And that was the thing that introduced me to the idea of beliefs. These students believed so strongly that empirical things determined the efficacy of constructions that they ignored the proof knowledge that they had. Similarly, what happened was I was trying to develop a scheme for coding what I saw when students worked on things. And my student assistants and I looked at a bunch of videotapes, and I realized that the students were going off on wild goose chases. Once they decided to pick something, they pursued it. So I had a problem where the students were supposed to determine the largest triangle that fit inside a circle. It is, as seems intuitively obvious, the equilateral triangle. But the students made that assumption and then worked on finding the area of the equilateral triangle until the videotape clicked off and they were out of time. When it did, I said to them, I'm going to tell you the area of the equilateral triangle. How does that help you solve the original problem? They couldn't tell me. And that's how I tripped over the issue of metacognition. So I started with teaching heuristics, taught a version of the problem solving course, and looking at the course, I tripped over metacognition, did more stuff built on that, wound up looking at beliefs when I realized that student behavior was shaped by their beliefs. And ultimately, after half a dozen years, came to the conclusion that I'd sort of reached closure in the sense that the knowledge base, problem solving strategies or heuristics, metacognition, and beliefs were the major things that shaped people's mathematical behavior. And what that meant was, first of all, those are the things I had to work on in problem solving courses, and that's what shaped the course and shaped my book. Second, it meant that if I was serious about having a long-term impact, I had to figure out how and where these beliefs came from. And that meant I needed to go into schools to observe instruction. One of my papers is called When Good Teaching Leads to Bad Results. Where that came from is I went into a 10th grade geometry class to see what students were learning about geometry. And in that classroom, this was also New York State, this was upstate New York, near Rochester at the time. New York had a Regents exam, which was a statewide exam. And on the exam, there were required proofs, you had to memorize them, and there were required constructions. You would get 2 points for replicating a construction that you had been told. There are 10 of them, one of them will be on the test. Well, what the school did was, because the constructions were based on memory, basically, it moved the unit on constructions to right before the test so the kids wouldn't forget. And I remember the teacher saying, you're going to have to know these things cold. Quote, you won't have time to think. Math isn't about thinking after all. And it'll be given full credit if the lines are where they're supposed to be. Well, that was the origin of the student's belief that what counts is the empirical accuracy and the theoretical stuff doesn't mean anything. So that got me more deeply into the study of beliefs and the origins of why students come into my university classes with the somewhat strange understandings of mathematics that they have. And those included things like theoretical mathematics is no good, has no utility in the real world. All problems can be solved in 5 minutes or less. Why? Another quote from that teacher, the test is going to have 20 problems. You've got 50 minutes. You've just got to crank out the answers. So the notion that you might spend an hour or two, much less 6 months, on a mathematics problem was totally alien.
Mm-hmm.
Part of what my research was about was figuring out what the features of school mathematics were that led students to develop the understandings they had, which were often counter to real mathematical thinking. And then now that I'd been in the real world, worrying about how do I begin to shape the factors that affect students and teachers and what goes on in the classroom so we can move things more in the directions we'd like to see happen. Because systemically, there are all sorts of constraints on what teachers do.
Yeah.
And that's actually what led me to look at assessment.
Yeah, that's where I wanted to go next too, because mentioning some teaching things, and I want to get to those eventually for sure. But it does feel like that Regents exam, the way the teacher's responding to the assessment, you kind of recognize at this point the power of assessment in shaping what's happening in school mathematics. So maybe tell us a little bit about the beginning of your work around assessment. Who are you working with, and how did you get started into that realm?
Right. Well, a couple of years before that, it was interesting. I was visited by someone who said, I'd like to talk to you about problem solving because I'm one of the people who puts together the Regents exams.
Mm.
We talked for a little bit, and I asked her, who puts the exams together? And she said, oh, it's a bunch of our teachers. How did you find out about me? Well, I happen to read about you, and I thought that would be interesting. Does anybody else on the committee know anything about problem solving? No. So it just turned out a somewhat random collection of people was making this exam that had huge impact on teaching and learning. That's sort of the background, systemic issues which persisted all the way through the Common Core and the two consortia to build those things, really shape what goes on in classrooms. So I did the problem solving work. I worried about my own assessment. And then in 1989, NCTM published the standards. They talked about problem solving. That was one of the four standards: problem solving, reasoning, connections, communication. It became clear, it was clear to the people who wrote the NCTM standards that problem solving should be in the curriculum. Although I will say it was largely misunderstood, and people talked about one-step problems and two-step problems, and they were still algorithmically driven. But the idea was problem solving is important. And NSF realized this. And at the time, Glenda Lappin was there, Joan Farini Mundy was there. And the first thing they did right after the standards was they said, we can't have teaching that looks like we like to see unless there are curricula that support that kind of teaching. And that was the first major inroad into curriculum development sponsored by NSF. They sponsored a dozen different curricula. This is the US. You can't tell people what to do, but you can give them good options. So they sponsored roughly four curricula at each of the elementary, middle, and high school level. And then they said, this entire effort is going to be doomed unless we have assessments that mirror the kind of teaching and learning we'd like to see. If the assessments are all problems that can be solved or exercises, they're not problems, exercises that can be solved in 2 minutes, and they reflect exactly what the students have been taught, and that's what testing has been to date, then nobody's going to teach problem solving. My friend Hugh Burkhart coined a phrase, it's WittyWig, what you test is what you get. If your test looks like garbage, teachers know their careers depend on it, their kids' careers depend on it. They're going to teach the garbage, the low-level drill and kill stuff. If your test looks somewhat interesting, then teachers and the kids, if it counts, if it's high stakes, will orient themselves at least somewhat to those things. So NSF put out an initiative for testing. And I got a call from Hugh Burkhart, who at the time ran the Shell Center for Mathematics Education at Nottingham. And Hugh said, Alan, the US needs assessment. We've been doing this for a large number of years. How would you like to be PI for an assessment project where we provide the horsepower? You don't have to do much, he said. And I said, why are you coming to the US? And he said, I live in Great Britain. You can't milk a barren cow. Uh, and I said, okay, that's cool. The only thing is, I never do anything as a symbolic head. If we're going to do assessment, I'm going to get majorly involved in this and be part of it. And in The initiative was 1991. We got a $3.5 million grant from NSF. That was a lot of money back then. And the goal was to create assessment materials that were consistent with the standards and that supported teachers in learning how to teach. The problem is, we were asking them to teach new stuff. They had no models for it, they'd never learned it, and they didn't have models for the pedagogy. So, what we wound up doing was two things. The first was we created a series of mathematical packages called balanced assessment packages. And these packages each contained roughly 20 very rich problems, descriptions of the mathematics in those problems, and then samples of student work that teachers could use to understand what represented student progress in thinking. This is what 2 points out of 8 are worth. This is what 4 points out of 8 are worth.
Hmm.
And basically, the idea was that those packages would be used to help support teachers in learning about teaching for problem solving. Alongside of that, over the years, we wound up building the Mathematics Assessment Resource Service that was in connection with Sandy Wilcox at Michigan State. And we wound up providing both professional development support for teachers that use the balanced assessment materials. And we designed, in partnership with David Foster at the Silicon Valley Math Initiative, a set of tests that could be used annually by school districts that signed up for them that focused on mathematical thinking and problem solving. And there's one very important finding out of that. I mentioned that if you test just basic skills, then teachers will focus on that. There's a flip side to that. If you have a test that only looks at basic skills and you have a rich curriculum, none of the values of the rich curriculum will be represented on the test. So you won't be able to show it made a difference. So those were the tests that we wound up building and using with David Foster. And there's a lovely little study in which David used both the California Standards Test and the Balanced Assessment Test, which is what it was called, either Balanced Assessment or MARS, on the same bunches of students. And it turned out you could do a simple 2 by 2 matrix. You pass or fail the balanced assessment, you pass or fail the California Standards Test. Only about 60% of the kids who passed the California Standards Test passed the balanced assessment. Now, all of those kids were certified by the state of California as being competent in mathematics. About 97% of the kids who passed the balanced assessment test passed the California state test. And that's because if you could pass the balanced assessment test and you had a rich curriculum, you could do that mathematical thinking. If you'd only been taught concepts and procedures, you could do well on the California test, but you'd die on the balanced assessment test. So we wound up using the balanced assessment test as both validation for and an impetus for teaching much richer mathematics.
And then I do want to go back into that teaching zone as well, because I know you have quite a bit of work on teaching. You mentioned the study that's very memorable once you read it, at least it was for me, when good teaching leads to bad results. You had toward a theory of teaching in context, you had models of the teaching process. And I know you also did a lot of thinking around the decision-making process. Like when the students were doing their problem solving, you were looking at the metacognition of the students. When you're looking at teaching, you contributed some ideas around the decision-making of teaching. So I wonder now if we could follow that thread into some of the ways that you studied teaching and what your ideas were around teaching, how those evolved a little bit.
Absolutely. So if you go back to the early 1990s, I've done the problem solving stuff. I've done a fair amount of professional development. Although one of the things that I learned there was most school districts they'll give you a day or two of PD, and that's it for the year. And I actually stopped doing PD at that time because a day or two is a waste of time. I could do a great Whiffy Jiffy workshop. I could get teachers excited about problem solving. They then go into their classrooms, try it, it wouldn't work, and they'd say, so much for problem solving. It's just a fad. So I did make the decision, if I'm going to do professional development, A, it's got to be research based, and B, it's got to be long term. I've got to make arrangements with a district that allow me to work with their teachers for enough time so that we can see real change. One thing I did know, and I still absolutely believe, the American system is crazy when it comes to teaching professionalism. Someone gets a bachelor's degree, they get a year of boot camp, and then they're sent off to their own classrooms, often isolated from other support. If you take teaching seriously, and I do, that's an outrage. What the Japanese understand is you can take the most talented beginner. It's going to take them a decade with support to evolve into a really accomplished professional. And they do that by making classroom behavior more transparent, by doing collective work, have teachers work together. And over a decade, as they reflect collectively and individually on their teaching, teachers get much better. What the Japanese didn't have, and what I spent a lot of time working on, was a formal theory of what counts in teaching. That's where I'll wind up. But if we go back to 1990, here I am, I understand problem solving, and I could construe teaching as an act of individual problem solving on the part of the teacher. That was one of the motivations. But the problem space is so much larger. The teacher has to know the content, has to know the students, has to take the temperature of the room, has to deal with all these other factors. In 1990, there was simply no way I could deal with that complexity in terms of the research. Far too complex for any serious theorizing. So what I decided to do was to do research on tutoring instead, because in that case, you've got a teacher whose goal is still to help someone learn, but it's a someone, it's an individual. And the content issues are more straightforward, the behavioral issues are more straightforward. Let me see if I can understand the decision making that the teacher engages in. I'm sure it'll involve the teacher's knowledge base, the teacher's metacognition, the teacher's beliefs. All of those will come into play. But let me see if I can figure out why teachers make the moves that they do, or why tutors make the moves that they do. That's actually using Polya's heuristic strategy. If you can't solve the given problem, try an easier related problem. So instead of n equals 30 students, n equals 1 student. My research group and I worked on that problem for almost 10 years because the goal was to actually build a model of the teaching process. Figure out how and why the teacher is making the decisions that the teacher is making. And there are various factors that affect that. If the student suddenly shows a gaping hole in their knowledge, the teacher is going to have to decide to address that and when to address that. If it's the beginning of a tutoring session, they may devote half that session to it. If it's at the end, they may make a note to themselves saying, I'll do it later. Then they're going to have to decide how. If the student says a squared plus b squared, a plus b quantity squared equals a squared plus b squared, are you going to tell the student? Are you going to do an area model? Or are you going to work through the algebra? What are the pluses and minuses of that? And how does the tutor decide which one to do? Well, it turned out the language that I used in describing this situation tacitly describes the architecture of a tutoring model. So let me do the translation. Basically, what happens is the tutor entered into a conversation with the student, did some assessment, and then established some goals. Okay, we're going to work through this problem first. Then, in interacting with the student, if the student got the right answer, it was cool. Teacher did an assessment and said, okay, that actually went pretty well. I'm going to try one that's a little bit harder. Or I think I need to reinforce something here. If something traumatic happened, like the student said a plus b quantity squared equals a squared plus b squared, the teacher said, whoa, those other goals get shelved for a while. I better focus on this one. What I've just described is a goal-driven architecture. So now I can describe it in general. Teacher enters into an environment, in this case with one student, does an assessment, establishes some goals, starts working on goal number one. If goal number one is reached, teacher says, great, goal number two. If goal number two is reached, great, sometimes you have a wonderful day. If something bad happens, then the teacher does a reassessment, and it can be on the basis of the content. Oops, student didn't know what I thought. Or it could be, I asked a question and the student got one of those deer in the headlights looks. I better back off and I'll save anything tough for the rest of the day. Well, there's your goal-driven architecture. I come in, I establish goals, I proceed on a given plan. If it works, I proceed to the next step. If it doesn't, then I establish a new goal and pick the way I'm going to try to get it. If that way works, great. If that way doesn't work, well, I have alternative methods. If it really gets bad, I bail and I do something else. If I succeed, I move to the next goal. And it turned out we could model all of our tutoring sessions that way. And then we realized, I mean, when I say we, all sorts of things happened to make it realize. Emily Van Zee came and joined our research group. She had worked with Jim Minstrel, who's a National Board Certified Presidential Award winning physics teacher. She had a video of Jim. And when we watched the video of Jim, I said, holy cow, he's doing the same things that are happening in our tutoring model. I bet you our tutoring model will work to characterize teaching. And I've already described the goal-driven mechanisms. Well, the teacher comes in with a plan. There are 30 kids there, and the assessment is complex, and the fire bell may ring, or the kids are having a bad day, or whatever, or something explodes in the content. But a goal-driven architecture still captures the teacher's decision-making. And as soon as I changed the frame to decision-making, I had a massive literature to draw upon, because in artificial intelligence, there's all sorts of stuff on medical decision-making. And it's exactly the same thing. You know, a doctor goes in to perform an operation and holy cow, there's a blood clot where I didn't expect it, plan B, and so on. So the theory of teaching from close to its origins became a theory of decision-making in highly technical, knowledge-driven, socially complex situations. And that's what led to the book, How We Think. At the same time, of course, I was in classrooms doing professional development and such. And problem solving was a corollary to that, because basically everything that counted in problem solving counted in teaching. Metacognition, well, how much time do I have for this? Am I going off on a wild goose chase? And everything that counted in teaching in terms of the decision-making being goal-oriented. What's my top-level goal? How do I choose sub-goals? Which one of those sub-goals do I pursue? When do I abandon them? Had a version in teaching and was an abstraction of decision-making during problem solving. So I viewed How We Think as a generalization of the work on problem solving. It was one continuous line that incorporated what was known about decision making, generally speaking. It was consistent with that entire literature, but focused on what teachers did in classrooms because that's what mattered.
Hmm. And bringing us roughly to the late 90s, going into the turn of the millennium there, I know you were also the president around that time of AERA, and you were, I think, a vice president of the National Academy. That could probably be a whole separate conversation. I'm sure there's stories from that era. But I want to sort of stay on this main thread of these key ideas in math education, math teaching and learning. I know you were involved heavily in the new NCTM project, which was the Principles and Standards coming around in 2000. I believe you were leader of in some role as the secondary level kind of person. So I wonder maybe if you could just share some of your recollections of being a contributor to that NCTM Principles and Standards effort.
I want to start by giving real credit to Joan Farini Mundy, who shepherded the whole process through, because it was a process that involved 25 writers in the context of trying to craft a new set of standards given what happened following the original NCTM standards, which was the math wars. It had become clear that the old standards were toxic. Any straightforward attempt to update them would probably be toxic as well. And that effort needed to be undertaken because over the ensuing decade, we'd gone from the point where handheld calculators were brand new and people were trying to grapple with the implications of that to the point where technological tools were readily accessible. And if you didn't reflect that reality, any standards document you had wasn't really valuable anymore. So the core ideas, we have content and processes. We have problem solving, reasoning, connections, communication. Let's add representations. We have an update of the content because statistics had become much more important. That all called for renovation. But then the question is, how do you do it and how do you affect the surround? And I'll tell you about one good thing and one bad thing. The good thing is that the leadership recognized what a political hot potato this was. So they did two major, use the word things again, to make sure they were viewed not as partisan loonies, but as being scientifically rigorous. First thing they did was they created advisory committees. They solicited information from all 13 mathematical societies about what do you do about proof, what do you do about any potentially controversial issue. And it was fascinating because when the AMS committee says do this and the MAA committee says do that, and they disagree with each other, then you have some evidence that there is actually controversy within the field.
Hmm.
Second, when Principles and Standards, which was the 2000 document, was produced, there was a letter from all 13 societies saying, we disagree with parts of this. Any group, any individual will disagree with parts of this. On the other hand, we completely endorse the process. We feel heard. We believe this was done with scientific integrity. So now you had all of the societies saying this was done right. So when you have one of the math wars standing up and saying this is a piece of crap, it's quite different because now it's not someone yelling with the authority of being, big professor at some place. It's one isolated person or 5 isolated people yelling while the math societies have said this is good. And the way they guaranteed it was good, I don't know if you know how the National Research Council produces its research volumes. It sends them all out for extended review. The reviews come back, and an auditor puts all the comments together and insists that the authors respond to every single comment. And the document isn't okayed until the review panel feels this has been done right. Well, NCTM hired the National Research Council to do that kind of review of principles and standards so that NCTM could say, if there was a problem, we sent out 80,000 copies of principles and standards for review. The National Science Council, National Review Council reviewed all of those. They okayed the process in the final version. So in terms of process, it was impeccable. And at some level, it ended the math wars. There was an editorial on the back page of the Chronicle of Higher Education by some of the people who had fought the math wars. And they said, we won, they listened to us, and they now did what we wanted. Meaning, basically, the current version was bulletproof. So that's the good story. The bad story, when we were putting the document together, I said to the group, look, people are talking about assessment. We're using the words problem solving, even though we have examples, people won't know what we mean. We need to have sample assessments for every grade band that demonstrate what we want students to be able to do. That way they can't pervert our words. I was voted down 25-1. The group just didn't want to go there. A few years later, George Bush was elected president. We got No Child Left Behind. We got dumbass tests, and they destroyed much of the value that we had in principles and standards in terms, and then in the Common Core as well. Because what you test is what you get, and the tests were largely garbage, and people weren't going to focus in classrooms on the things that weren't on the tests. So my one regret is that I wasn't able to convince the standards writing team that part of the rollout needed to be assessments that were reflective of the values we had for the NCTM standards volumes.
Seems like with every big undertaking, there's just even more undertaking that has to go along with it, right?
That's why I've been at it for 50 years.
Yeah. Well, and you also have a knack for getting right into the middle of some tense areas. Another one is the What Works Clearinghouse. So kind of also in the same vein of what's the national policy context, how is research being evaluated, what counts as evidence in math education. You wrote an influential paper where you critiqued What Works Clearinghouse in pretty strident terms. I wonder if you have just some recollections about that. I know this could again be another conversation, but I can't let you go without hearing a little bit about what you think about What Works Clearinghouse and what's happened since that paper.
Yeah, it is a long story, so I'm going to try to condense it radically. Part of No Child Left Behind included not only math, but literacy. And the people in the Department of Education had focused on literacy, and in particular had taken a hardline pro-phonics stance as opposed to whole language. And one of the interesting things about assessment is that it's much easier to assess basic skills than it is to assess complex thinking. So they had all sorts of rigidly controlled research studies that showed how much learning there was using phonics. That also in math ed you could find showed, geez, if you do drill and kill, kids learn exactly what you teach them. And if you test them on that, they do okay. So when What Works set up, it said, we are going to look for tests that are truly rigorous, and we will only count those as the gold standard for accrediting, if you will, curriculum. And it turned out that, well, as I mentioned, there were hardly any studies that met their criteria, whether in language arts or in mathematics. And in language arts, they were almost all phonics, and they proved that phonics worked. And in math, the few tests they had that got certified basically showed that skills-oriented curricula did well. There were between half a dozen and a dozen that got their accreditation in math. I don't remember how many precisely, but it was on the order of 10. Well, there's a lot of, again, little bit of background. You might ask, why was I chosen to do this? Because I'd been involved in a number of things that clearly featured math understanding. One of the things I've always focused on is being rigidly scientific and never making any claims that you can't back up. And my feeling is, this is just guesswork, that the people who put together what works said, Schoenfeld's going to tell the truth. We believe that straightforward math education will win. If it does, he will tell people that. And if there's no rigorous evidence for thinking and problem solving, he'll tell people that. So we think we're safe here. So that was the context within which I joined What Works. And I said, I'll write some materials for you. I'll describe the background, and then we'll look at the tests. And as I said, maybe 10 of the tests met their certification standards, which all had to do with the rigorousness of test design. And I said to them, you don't have any content analyses. You're not saying anything at all about what the tests actually test. And they said, we can't afford to do those analyses. That's a big undertaking to look at what's in each test. And I said, no, it's not. You've got 10 tests that met your criteria. And they absolutely refused to do it. So I looked at them and they were all drill and kill. And they were coming to write a publication about what works and what it did. And they said, okay, you write it. And I wrote a draft that said, here's what we were looking for. Here's what was done. Here's the problem. They needed to do content analyses and they didn't. From my perspective, then, this does not adequately represent what assessment is. And what they did was they shut down the volume and they shut down another volume, basically denying me access to publish that. And that's why I went to AERA and wrote the story. What happened? I'm actually surprised that you know it because mostly it sank without a ripple. Some academics said, oh yeah, but it was more larger politics that the strict phonics work and the drill and kill math work sort of faded away until the renewal of the phonics controversies of the past year or two. But I don't think that my work played any significant role in that.
But still appreciate hearing from your perspective and trying to do what you could to sort of shed a light on what was going on there. And I do think it made an impact, at least in the math ed community, that it kind of confirmed some suspicions, I think. And then to hear it from you, sort of a person that had saw it from your point of view.
Yeah, well, the main thing I think is, again, I mean, the real world is messy. So, and you have to deal with that fact. But as much as possible, you want to be able to do things that are rigorous, will stand the test of time, and that reflect your values in terms of inquiry and are honest. Why that's important is it's going to be important when we look at assessments of what goes on in classrooms. If we want to both document learning, that's what the earlier tests, the MAC tests, the balanced assessment test did. And if we want to use some form of assessment of teaching as a reasonable way to enhance the teaching process. So overall, we need to keep those things in mind as we move forward. That's an ongoing issue.
Yeah. And that brings us to the last kind of chunk of your work that I want to talk to you about, which is the mathematics assessment project and the true framework, teaching for robust understanding. So maybe you could just let us know, how did the mathematics assessment project come about, and what are some of the ideas that are coming forth from that effort, which I know is a continuation of a lot of the stuff you've been sharing about.
Yeah, there are actually two parts that got closely wedded. As I mentioned before, my assessment work with the Shell Center began in 1989. It began with preparing materials for teachers that would help them understand and teach for problem solving, because there's an issue of scale, there's an issue of knowledge. The question is, how do you get started bootstrapping that knowledge for large numbers of teachers? And the answer was build materials that help them teach, build assessments that respect your values, that show whether or not those things work. We did that starting in 1991. That was balanced assessment. We moved to the Mathematics Assessment Resource Service, or MARS, and we kept going with funded grants, mostly through NSF at that time. And then now, about 15 years ago, the Gates Foundation got interested in math ed, and they said, we need exemplary curriculum materials that also serve as a basis for assessment. And here I want to give the lion's share of the credit for this to Hugh Burkhart and Malcolm Swan at the Shell Center at Nottingham. Once again, this was an American product with a British steam engine. We'd been collaborating for more than 20 years. So the question was, how do we build a team that builds and studies exemplary units? Malcolm, who to my mind was the world's best designer, I rarely use the word genius, but he was one, had some ideas about putting such materials together. We worked largely with David Foster at Silicon Valley Mathematics Initiative. If you're really going to do instructional design, you do multiple iterations. I mean, typically what happens is people get money, they sit down, they write a version of a book or something else, they try it out with one round. It's called alpha testing, beta testing, and it's out. If you really want to build robust instruction and you want it to work in a variety of circumstances, like well-provisioned schools in Silicon Valley to schools in the upper Michigan Peninsula that don't have very many resources, to et cetera. What you've got to do is build a draft, have it gone over by a whole bunch of people, try it out in classrooms across the United States, have trained observers take notes on what worked, what didn't, and why they think it worked the way they did. Bring it back, assign it to a second design team because the first design team is too invested in what they did. Go back, do that whole process over again, in some cases 3 or 4 times. The net result is it costs about $50,000 to develop a 2 to 3 day lesson. That's an investment no publisher was willing to make. But Gates said, we will give you the money to develop 100 of these lessons. It was 6 million more or less, with the professional development support, so that these are 2 to 3 day lessons. It's 20 days a year for grades 5 through 10, more or less. So we're generating lessons that cover 20 days out of a year. And we did. Gates trusts nobody, so without telling us, they sent people into Kentucky to do evaluations of what we were doing. We got a call from our program manager who said, hey, Alan, we just got some results from Kentucky. You want to hear about it? I said, do tell. I had no idea. And she said, basically, Crest at UCLA and Research for Action studied what was going on. The base conditions were an average of 4 to 6 formative assessment lessons per year, which translated to 10 to 12 days of instruction. What Crest did was they formed a measure of mathematical understanding, sort of like reading tests. You rated grade 7.2 at the beginning of the year. If you read at grade level 8.5 at the end of the year, gee, you learned a lot. If you read it grade level 7.5, it was a bad year. They created that kind of measure. And what they discovered was in the Kentucky classrooms where teachers used between 4 and 6 of the formative assessment lessons, there were average learning gains of 4.6 months. My first reaction was, no way. My second reaction was, of course, that's what happened, and I know why, because we designed it that way. Yes, problem solving was a key part of it, but what made the formative assessment lessons work was the pedagogy. Because basically, we would take a problem that was extremely rich, that was part of the design, give students a chance to work on it, but instead of the teacher then saying, here's how you do it, the teacher had been told with a 20-page lesson plan, here's what to expect. Here are some things you might do, getting the students to talk to each other or other such things that might enable them to make progress. Here are some things you might do with the students that might enable them to make progress without giving the game away. And the net effect was that the formative assessment lessons changed the teacher's pedagogy. We went into a teacher's classroom and observed what happened before, during, and after each of a half dozen formative assessment lessons. First one, teacher taught the way she normally did the first formative assessment lesson, kind of clumsy because they weren't invested in it. Afterward, taught exactly the way they had before. Second one, they'd studied a little more before, exactly the way they had taught. During a little better implementation, afterward, the teacher asked a question or two. Third, there were more questions afterward. By the end of the year, the teacher was doing half as much telling and twice as much questioning and supporting conversation. That was the change in pedagogy that led to increased student learning. Okay, so there's the development side. And the development, again, was led by Malcolm Swan, and it was brilliant. On the research side, I had reached the point where I knew what good thinking was mathematically. I knew what problem solving was. I knew some of the things that teachers did that were effective or ineffective. But what I didn't have yet was a sense of what made the learning environment powerful. And that was different because now you're talking about the characteristics of an interactive environment rather than a goal-driven architecture which explains either student or teacher thinking. So we went back to the drawing board and we studied the literature on teaching. You'll find literally 300 different things that contribute to powerful classrooms. So I'm a mathematician. I wound up looking for equivalence classes. See if you can distill those down into categories that are powerful. We had all sorts of mishaps, but basically we wound up with somewhere between 4 and 7 categories of things that seemed important. And then the question was, how do we get empirical evidence that these distillations make a difference? So we went into classrooms and tried to develop a coding scheme, iterated between coding, watching videos, or living in classrooms, and seeing how things actually played out in terms of the scores and what we thought was going on in terms of student learning. We wound up with 5 categories of behavior that were necessary and sufficient. That's the teaching for robust understanding framework, or TRUE. The first one, not surprisingly, is the mathematics. If the math isn't good, if you're just doing rote mathematics, that puts a cap on what kids are going to learn. So if the math isn't good, you lose. Second is cognitive demand. How hard are the kids working? The weightlifting analogy is if you lift 1 pound weights, you're not going to build muscles. If you try to lift 500-pound weights, they won't come off the ground and you won't build muscles. You need to be working at a level that stretches you so that you build your mathematical muscles. The third and fourth, which are really put together, are equitable access to the content and three things lumped together: agency, ownership, and identity. We really care about classrooms that every student learns in, every student has the opportunity to learn in.
And their ideas are welcomed into the classroom space.
That's right. That's where issues of identity are absolutely central. If you're afraid to contribute, you're not going to engage, you're not going to learn. So equitable access, if there's a way the kids can hide under the desk, things aren't going to go well. If the teacher calls on the same 3 kids, the math may be beautiful, but n-3 kids aren't going to learn. So access provides the opportunity for engagement. But the question is then, what kind of engagement is there? And that's where kids need to be welcomed into the space. There need to be opportunities for them to build on others' thinking and for others to build on their thinking. And in that way, for them to build identities as people who can engage, who can do mathematics. So this is where, although it may seem at first that it looks different, all of the earlier research on beliefs comes into play. If the only experience you've had with math is the teacher tells you what to do, then you don't come to believe that you can create mathematics. If you experience mathematics in such a way that you conjecture that some of it turns out right, but you're helped to fix it and you're helped to build on what is right, then you're engaging in the doing of mathematics in ways that helps you build a productive mathematical identity. So we have the mathematics, cognitive demand, equitable access, agency, ownership, and identity. And then the question is, how does all this come together? And the glue that holds together the powerful classroom is formative assessment, because the teacher's watching what goes on and nudging things where they need to be nudged. So if the math is too hard, or if the math isn't beautiful, do something about it. If it's too easy, make it tougher. If it's too hard, find a pathway that'll get the kids to the rich mathematics. The rich math remains the goal, but formative assessment helps you get to the rich math. If you're watching what goes on, you can see whether kids are bored or whether kids are struggling. And you can use formative assessment to adjust cognitive demand. If you see kids fading out, you can lure them back in. You can build for engagement by more kids by picking rich tasks that can be done in a variety of different ways that have different entry points. Then you can support kids in talking about each other's way of looking at the problem. Those are ways to get equitable access. Everybody has a way into the problem, and everybody has a way into the conversations, thanks to formative assessment, which then get all the kids involved and provide opportunities for the construction of productive identities. So formative assessment is what makes the other 4 dimensions work in rich ways. So the 5 dimensions of true again are: the math has to be rich, kids have to be stretched, cognitive demand, every kid needs to have opportunities and support in engaging, that's equitable access. They need to engage in ways that enable them to be and see themselves as mathematical productive, that's agency, ownership, identity. And the teacher needs to be on guard for the opportunities to make all those things happen. Guess what? that's the abstraction of decision making, including metacognition. So, true in that sense is the culmination of that previous work. Now, Malcolm was designing in ways consistent with that for the formative assessment lessons. What I was doing was the research component. First thing was distill things down. Second was build a coding scheme. How do we see these things in classrooms? So we came up with a coding on what's now a 0 to 5 scale of classroom for each of those 5 dimensions. Then it turns out that in the Mathematical Effectiveness of Teaching project, or the MET project, the Gates Foundation had hundreds of tapes of classroom interactions. And they had wanted to assess the students in them, so they had balanced assessment scores. They just chose the best assessment around, and it happened to be ours, but it had nothing to do with their choices. As a matter of fact, it took me months to get permission to look at their tapes. But we got access to their tapes, and that meant we could code the tapes, assign them scores, look for correlations between the scores of those classrooms and the students' performance on the balanced assessment tests. And things worked exactly as we'd have hoped, which is the better classrooms scored on each dimension of our true rubric, the better the kids performed on the balanced assessment test. And on the one hand, we had my research, and then we went into classrooms that were using the MAP lessons, of course. And there was a really tight relationship between the values exemplified in the MAP lessons and the 5 dimensions of true. So on the one hand, our MAP package was entirely consistent with the best of our theoretical understanding. On the other hand, as with everything else, we had some rigorous empirical evidence that these things really did work when you did this kind of stuff. Only took 50 years to get there.
Well, I really appreciate hearing about it and being able to follow the trajectory of your work and exciting that you have kind of, arrived at this nice kind of culmination of things where a lot of the threads are coming together. That's kind of amazing on its own. It also makes sense to think about the awards that you've received for your career. The Klein Medal, I know, is probably a pinnacle for you from the ICME, International Award for Math Education, Lifetime Achievement, and other awards from Mathematical Association of America. So many things. Really great career. I've really appreciated talking with you. I have a few closing questions that I do want to ask. Some that are, still leaning into your research perspective, and then a fun one to end. So first of all, I know you've, kind of entered a sort of phased retirement, but you're still doing some work and still have some, postdoc and doctoral students that you're working with and still finishing some of your analyses. But is there still a research question that's on your mind or kind of a piece of inquiry that you're like, oh, I still can't quite let go of that's, tickling your fancy in that way?
Yeah, there are 2 kinds of things, one of which is utterly hopeless, the other of which I'd like to influence. Many years ago, I wrote a piece for AERA about making change. And at that time, National Science Foundation was spending about $7 million a year on improving STEM education. I think it was Purina Dog Chow that spent $200 million a year on research for pet food that would improve dogs' health. 30-to-1 ratio. And the problem is that we have never been serious about making the investment in education that the United States should make. And the one thing we have is empirical proof that the formative assessment lessons produced by the MAP project make a difference. They're far from perfect, but what we had was significant changes in pedagogy. And although the baseline numbers were pretty terrible, so improvements look better than they actually are, evidence that the lessons made a decidedly non-trivial improvement in student learning. That was at a cost of $6 million for 10 to 12 days of the school year. 180 days school year is 18 times that. So you're talking about 18 times 6, which is a little over $100 million. For an investment of a little over $100 million, you could get a well-tested curriculum from K through 10. Well, we did 5 through 10. So for $100 million, you get 5, 6 through 10. Double that, you get the whole curriculum. $200 million? You know, pharmaceutical companies spend that much money on lost products all the time. We're not serious. We went to Gates and we said, we want to do more of these. They said, been there, done that. We went to the NSF. They said, nope, not our thing. Curriculum development got us into trouble with the math wars. So we have mechanisms for improvement that are simply going to sit on the shelf because there isn't the wherewithal to make a difference. And that's extremely frustrating. It's not as if we're starting blind. We know enough in terms of assessment. We know enough in terms of curriculum development. We don't have the infrastructure, although the map materials could help with regard to building professional development. It's all a matter of willpower in a country that hasn't made this a priority. That I find truly saddening. When it comes to things I'd like to pursue, truth still a skeletal framework. At the top level, it says these 5 dimensions are important. To the degree that each one of them takes place in a classroom, kids will have a richer experience and learn more. Pick something that matters. What about mathematical language? Well, where is mathematical language in true? It's not in the headlines. That's because I could only pick 5 headlines. On the other hand, you're not going to have rich mathematics unless kids learn to talk mathematics in the language of mathematics. But that formal language of mathematics is going to be an obstacle to some, and the pathways to it through cognitive demand, through equitable access, are going to be really important. Agency, when a kid can express him or herself in a way that makes sense and then convert that to math and have real rich mathematical conversations, then you're going to get a sense of agency. And formative assessment is entailed in all of that. So underneath the top dimensions, there are loads of things that be elaborated. Now, there's a German colleague of mine who's working on issues of language. She would like to have it be a 6th dimension. I resist that because of George Miller's The Magic Number 7 plus or minus 2. 5 things is as much as people can hold in mind. But that's an example of something that really needs to be elaborated. And if we could make progress examining rich classrooms using rich curricula and study both teacher learning, how do we understand teacher trajectories when they have opportunities to learn, both from the materials and with the support of good teacher communities, and student learning. That's what I'd like to see. If I had another 50 years, that's what I'd be working on.
Hmm. And so you may have just answered this, or in a way you did, but I'm going to ask it anyway. Do you see a key problem that the rest of the field needs to take on? So it's maybe the same thing that you're still interested in, but it also could be something that other people need to work on. It doesn't have to be you.
Um, that's basically my answer, but let me do a little sidebar. Because education has always been the field of fads. And it's easy for us to be distracted. What I wound up talking about and highlighting what I think matters is what I think should drive us for a long time. Some people would say, in response to that, are you still living in the 20th century? What about technology? What about artificial intelligence? I have 2 answers to that, which will spring off the first one. When I got started, I mean, I actually had a slide rule when I was an undergraduate. And I worked on, I was the first generation to work on the kinds of computers that had massive drum card readers. And I do my programs with a stack of cards that was a foot tall. When calculators came in, the question people all asked was, what can we do with calculators? How can calculators shape mathematics? And that is profoundly the wrong question, because the question should have been, what do we value in mathematics and how can we use calculators to enhance students' mathematical experience? So an example of that is that when I took my first stats course as an undergrad, every distribution we studied had a variance that was a perfect square because we needed to create the standard deviation, which was the square root of that. That meant every single problem we worked was artificial. Now you give me Excel, then you give me a handheld calculator. I can go out and do real world problems and crank out the standard deviation with no trouble. So the question should have been, what does the technology offer to make the mathematical experience richer? We're going to hear a whole lot of crap about artificial intelligence. And the question should be the same. We're in a time of really growing technology. We're also in a time of technological risk because you can't trust the technology anymore. So the question is, how can we harness the technology to make people's mathematical experiences richer? How can we harness the technology in ways that actually enable us to make forays into the real world and do things with the applications of mathematics we couldn't do before? How can we do that responsibly? And those are questions that will need to be addressed alongside the ones that I just mentioned.
All right. Well, thanks again. I do have a final question that I want to ask. It's to imagine this whole entire career of yours just went away. And what if you did something else as a career? Is there something that you could imagine in an alternative sort of universe?
Right.
And you can't just say mathematician or staying in pure mathematics.
Well, aspects of it are more likely to happen now than as a career replacement. I was born to be an academic, but I'm going to
Okay.
write academics off as a possibility. So I can't replace a 50-year chunk.
Okay.
Those who know me will tell you that my most frequent metaphors when I'm explaining things in my research group have to do with food.
Mm.
I'm very serious about food, also pretty serious about wine and coffee, but a good half of my research metaphors outside of formal papers have to do with food, although I did write a paper you may or may not have run across called Making Mathematics and Making Pasta from Cookbook Procedures to Really Cooking. That paper was about the fact that when you're really cooking, you don't rely on recipes. You rely on the feel and texture of the materials and what you know. Bakers will tell you the same recipe won't work for a cake on a wet day and a dry day.
Mm.
I learned that the hard way when I first rolled out my first piece of pasta dough because it was extremely dry and I couldn't get the dough to work at all. Years later, I actually make the dough in a food processor and it's all by eye. There are no measurements whatsoever. That's the same thing as in mathematics. There was a lovely paper by Lara Alcock that showed that if you give estimation tasks to mathematicians and you give them again 6 months later, a large percentage of the time they use a different method.
Mm.
What it means is they have a sense of the whole terrain. It's all interconnected and all those things come together.
Mm-hmm.
So I've been a foodie from day one. My wife tells the story of when we took a cooking course in Cambodia on cooking Cambodian food. The chef came around and said, I need to help you with the knife work. I need to help you with the knife work. You're fine. That was uh, when my postdoc is done, when my last official student has got her PhD. As a pipe dream, I might think about culinary school because I know I can be better. In the meantime, it's my job often if there are just random leftovers in the refrigerator. My wife says, Ellen, it's your job to make something reasonable out of those. So I'll continue playing, but if this were to be a fantasy, I know the world of cooking is different and I wouldn't have any hopes of being a chef. But I could be a home chef and have spend a lot of time having fun.
Yeah, great. Well, Alan Schoenfeld, thanks so much for being the guest to kick off this season. And I've been reading your work for decades now, and it's just been really great to hear from you directly and to get those insights on the sort of story of your work. So thanks so much for sharing it.
Absolutely, it's been my pleasure, Sam. Thanks for inviting me to do it.